Welcome to Talk Tensors.
Glad to be here for this one.
Yeah, on this deep dive, we are covering a really foundational AI safety and alignment research paper.
Very foundational.
But before we get into the actual technical architecture, I want you to just imagine a scenario for a second.
Okay.
Picture a world where a brilliant, hardworking student spends weeks crafting this original, deeply researched essay.
Right. Synthesizing complex sources,
Yeah.
doing the real work.
Exactly. They refine their arguments, they submit their work, but instead of a grade, they get called into an academic integrity hearing.
The worst nightmare.
Right. And they are threatened with expulsion, and the sole piece of evidence against them is a black box algorithm.
An AI text detector.
An AI text detector that has flagged their completely original human-written work as machine-generated.
Yeah.
And the student has no cryptographic proof of their own human authorship, and the institution just blindly defers to the machine's binary classification.
Which sounds like speculative fiction, I know.
It really does. But this is the current high-stakes reality. I mean, educational institutions, enterprise compliance departments, major online platforms.
They're all aggressively deploying these AI text detectors.
Right, as a defensive shield against this massive influx of machine-generated content. But the real question is, are these classification systems actually providing the rigorous security they promise?
Or are they just a fundamentally flawed architectural illusion?
Exactly, an illusion that introduces catastrophic vulnerabilities into our information ecosystems.
And that tension, that exact tension, is why this specific area of alignment research is so critical right now.
Yeah.
The reliable identification of AI-generated text, it isn't just an academic curiosity. It is a foundational pillar for maintaining the integrity of digital infrastructure.
Because as generative models scale in parameter.
And capability, yes.
Yeah.
The threat models expand exponentially. The safety community is looking at the automated proliferation of zero-day phishing campaigns.
Highly personalized social engineering attacks at scale.
Exactly. The algorithmic fabrication of synthetic news, the pollution of training data pipelines with recursive machine-generated noise.
It's a lot.
It is. And the underlying assumption driving the deployment of these detection systems is that we can enforce a baseline of cryptographic or statistical authenticity.
Right. If we lose the ability to differentiate human from machine in the text space, we lose a primary defense mechanism.
Against automated malicious scaling, yes.
Okay, let's unpack this. Today's mission is to analyze the underlying architecture of these detection methodologies.
By unpacking a really landmark paper from researchers at the University of Maryland.
Yep, Savan and colleagues. We are going to put the entire paradigm of post-generation text detection under the microscope.
And their thesis is pretty uncompromising.
It really is. The authors demonstrate that as large language models continue to scale and approximate human text distributions, detecting their output becomes a mathematical impossibility.
A literal impossibility.
Furthermore, they prove that the current state-of-the-art detection frameworks deployed in the wild right now can be systematically dismantled.
Evaded, or even weaponized by a motivated adversary.
So we need to structure this analysis rigorously to understand the full scope of the vulnerability.
First, we will examine the 4 primary pillars of AI detection.
The specific methodologies currently serving as the industry standard.
Second, we'll analyze the evasion vectors, focusing heavily on a technique called recursive paraphrasing.
And look at the empirical data on how it just degrades detection accuracy.
Third, we will explore the implications of spoofing attacks, where adversaries actively manipulate these systems to frame innocent human authors.
And finally, we will dive into the core mathematical proofs,
Specifically focusing on total variation distance.
which formally bounds the limits of any possible detection system. So let's start with the architectural landscape.
The baseline.
Right. Before this specific research disrupted the consensus, what were the primary engineering approaches being utilized by the safety community?
Because the market is saturated with proprietary APIs claiming near-perfect classification accuracy.
Right, and we need to understand the mechanics under the hood.
Well, the alignment and safety community had effectively categorized the detection problem into 4 distinct engineering approaches.
The 4 pillars.
The 4 pillars. The first pillar consists of neural network-based detectors.
Okay.
The architecture here usually involved taking a robust, pre-trained transformer model, often a Roberta-based classification head, and subjecting it to extensive supervised fine-tuning.
So training a model to catch a model.
Basically, the training corpus is a massive labeled data set of human-written text and AI-generated outputs.
And the objective function.
It's designed to force the model to map the subtle, high-dimensional statistical differences between the two distributions.
It is essentially training a discriminative model to identify the latent topological features of a generative model's output.
Exactly.
But wait, doesn't that inherently introduce a severe distribution shift vulnerability?
Oh, absolutely.
Because if you are fine-tuning a Roberta discriminator on data generated by, say, GPT 3.5, its classification boundaries are optimized for that specific latent space.
Right.
So the moment an adversary switches to Claude 3 or a fine-tuned llama model with a totally different temperature setting, your trained detective is suddenly operating out of distribution.
That is the primary architectural limitation of the first pillar. It requires perpetual reactive retraining.
Which is computationally expensive.
And always leaves the defender one step behind the adversary. Which brings us to the second pillar.
Zero-shot classifiers.
Right. Frameworks like DetectGPT. These operate without the need for a supervised fine-tuning pipeline.
So no retraining.
No retraining. Instead of learning a classification boundary, they analyze the inherent statistical properties of the text passage directly.
Specifically evaluating the per-token log probability evaluated by the source language model itself. I want to dig into that mechanic, actually. When we talk about zero-shot classifiers analyzing the log probability, we are looking at how predictable a sequence of tokens is to the model.
Yes.
How exactly does DetectGPT differentiate between a highly predictable human sentence and a highly predictable machine sentence?
It relies on the geometric properties of the probability space. The researchers operate on the hypothesis that AI-generated passages tend to sit in the negative curvature regions of the log probability function.
Okay, unpack that geometry for us.
Sure. If you take a given text sequence and apply minor random perturbations, essentially swapping out tokens using a masked language model like T5.
Just changing a word here and there.
Right. The log probability of the perturbed text will drop significantly if the original sequence was generated by an AI.
Because the AI's original output is essentially a local maximum in that probability space.
Precisely. It was highly optimized. Human text, on the other hand, is much more statistically anomalous.
So if you perturb a human sentence,
the log probability might fluctuate randomly or even increase.
Because the original human phrasing wasn't optimized for the model's likelihood function to begin with.
Exactly.
That makes a lot of sense. It's essentially testing the fragility of the sequence's likelihood.
Yes.
If slightly altering the text causes the probability to plummet, it means the sequence was highly optimized, which is the signature of a machine generation.
You got it.
So that covers the supervised discriminators and the zero-shot probability analyzers. What is the third methodological pillar?
The third pillar is watermarking, specifically the soft watermarking protocols popularized by researchers like Kirchenbauer.
Oh, watermarking.
What's fascinating here is that the watermark operates invisibly at the algorithmic level during the actual generation phase.
It utilizes concepts closely related to cryptographic hashing, right?
Yes. During the decoding process, as the AI selects tokens, a hidden pseudo-random number generator, or PRNG, is deployed.
And this PRNG is continuously seeded by the hash of the preceding token.
Correct. At every single generation step, the PRNG dynamically partitions the model's entire vocabulary space into a green list and a red list.
So dividing the dictionary in half, essentially.
Yes. And the decoding algorithm is then mathematically biased to artificially inflate the logits of the tokens residing on the green list.
So instead of trying to detect a naturally occurring statistical signature post-generation, the developers are actively embedding a steganographic signal into the output distribution.
Exactly. A human reader parsing the text notices zero semantic degradation.
But a detector possessing the specific cryptographic key for the PRNG can rebuild the exact token partitioning sequence.
It simply counts the frequency of greenlist tokens, and if that frequency violates the null hypothesis of standard human vocabulary selection, it flags the text.
The statistical confidence of soft watermarking is immense.
It really is, because you are artificially skewing the distribution. The probability of a human writer accidentally mashing the greenlist token sequence across a 500-word essay is astronomically low. In tightly controlled, closed API environments, Soft watermarking consistently achieves a true positive rate exceeding 99%.
While maintaining a false positive rate of less than 1%.
It was widely considered the most robust defense mechanism available.
Assuming you could compel the foundational model developers to implement it at the source.
That is the catch.
Which brings up the obvious deployment friction. Open weights models completely bypass that defense.
Because anyone can strip the watermarking logic out of the inference code?
Right. But assuming a closed ecosystem, watermarking is the gold standard. What is the fourth and final pillar they analyzed?
A fourth is retrieval-based detection.
Okay.
Systems proposed by Krishna and others abandon statistical inference entirely in favor of a brute force data architecture.
Just logging everything.
Yes. The methodology requires the deployment of a centralized, massive-scale database that logs every single interaction and generated output from the LLM. When an external query is made to verify a piece of text, the detection system uses advanced similarity search algorithms, often Bayes indexing, to hunt for semantic matches within the log database.
So if the cosine similarity between the queried text and a logged output crosses a specific threshold, the system definitively attributes the text to the AI.
Exactly. It's a deterministic check.
The computational and storage overhead for maintaining a real-time semantic index of every generated token across millions of users seems staggering.
Oh, it is.
Not to mention the massive privacy and data residency implications.
Huge implications.
But theoretically, it provides a deterministic answer rather than a probabilistic one.
Right.
So these are the four pillars: supervised neural networks, zero-shot log probability analysis, steganographic soft watermarking, and brute force retrieval logging.
And the industry consensus treated these frameworks as highly reliable.
Highly reliable. So how exactly does the research team go about dismantling them?
The researchers approached this not through theoretical modeling, but by executing rigorous empirical stress tests.
Simulating a highly motivated adversary.
Yes. They designed an evasion vector known as recursive paraphrasing.
Recursive paraphrasing.
The fundamental concept is akin to adversarial perturbations in computer vision,
where adding calculated noise to an image can force a convolutional neural network to misclassify it.
Exactly. But here, the perturbation happens in the discrete semantic space of natural language.
So it's like money laundering, but for words.
That's a great way to put it. An attacker uses a foundational model, perhaps one that is heavily restricted or watermarked, to generate their target payload.
Be it synthetic propaganda, academic fraud, SEO spam.
Right. But before deploying the text, they pipe that output through a secondary independent language model specifically optimized for paraphrasing.
Effectively scrubbing the original statistical and steganographic fingerprints.
Yes.
And the recursive aspect implies this isn't a single pass operation.
No, not at all.
They are iteratively feeding the output back into the paraphraser. You rewrite the text, then you rewrite the rewrite.
Compounding the semantic transformation to distance the final output from the original likelihood distribution.
What was the exact experimental setup for this laundering pipeline?
The methodology was incredibly thorough. They initiated the generation phase using a variety of foundational architectures.
Like OPT 1.3b, OPT 13b, and various iterations of GPT-2.
Yes. They targeted a generation length of approximately 300 tokens.
Okay.
Crucially, they didn't just test this on generic conversational data. They built the evaluation corpus across highly distinct perplexity distributions.
So different types of text.
Right. They used the XSUM dataset to simulate highly stylized journalistic prose.
The PubMed QA dataset to introduce dense, specialized medical terminology.
And the Kafka dataset for standard business and marketing copy.
Which is smart because that ensured the evasion metrics weren't artificially inflated by a specific linguistic domain.
Exactly. Testing across diverse domains is vital.
Because medical literature is naturally going to have a much tighter, more predictable vocabulary distribution than creative writing, which affects the baseline log probability.
Yes, it does.
What models did they utilize for the actual recursive paraphrasing engine?
To ensure the paraphrasing was robust enough to alter the statistical signature without destroying the underlying semantics, they required heavy compute.
So not just a simple script?
No. They utilized DIP-per, an 11 billion parameter model explicitly fine-tuned on diverse paraphrasing tasks.
And Lame27B chat.
Yes, a highly capable 7 billion parameter instruction-tuned model They also benchmarked a lighter T5-based paraphraser for comparison.
So they took the AI-generated payloads and recursively passed them through these secondary models up to 5 distinct times,
iterating the temperature and top sampling to maximize lexical diversity.
Okay, let's look at the degradation of the detection systems. When they ran this recursively laundered text back through the 4 pillars, how catastrophic was the drop in classification accuracy?
The degradation was absolute across every single methodology.
Right.
Let's start with soft watermarking, the supposed gold standard.
Right.
Prior to the adversarial paraphrasing, the watermark detectors successfully identified the generated text with a true positive rate of 99.3%.
Pegged to a 1% false positive rate.
Yes. After 5 recursive passes through the LeMay 2 paraphraser, that true positive rate collapsed to 9.7%.
That is insane. The steganographic signal was entirely overwritten.
Completely.
A drop from over 99% to under 10% means the system is effectively nullified.
Nullified.
What happened to the zero-shot classifiers, like DetectGPT, that map the curvature of the probability space?
DetectGPT relies on the geometric fragility of the original sequence.
Right.
But the paraphraser restructures that sequence, moving it out of the local maximum of the source model.
So for DetectGPT, the primary metric is the area under the receiver operating characteristic curve, the AURC.
Yes. And as a reminder, an AORA of 1.0 is perfect classification.
And 0.5 is a random coin flip.
Right. DetectGPT began with a highly robust AORC of 96.5% on the baseline text.
And after the recursive evasion,
it plummeted to 25.2%.
the system was completely disoriented.
Completely.
And the retrieval databases. If you are semantically rewriting the text 5 times, you are drifting away from the original cosine similarity threshold.
Precisely. The brute force retrieval systems dropped from 100% deterministic accuracy down to below 60%.
Even the supervised neural network discriminators, like the fine-tuned Roberta models,
they saw their classification accuracy regress toward the mean, dropping from near perfect levels down to the 60% range.
So the recursive paraphrasing effectively homogenized the latent statistical signatures that all 4 pillars rely upon.
It did.
But this raises a highly critical architectural question.
Okay.
If you take a coherent sequence of 300 tokens and recursively pass it through an 11 billion parameter model 5 separate times, forcing lexical substitution at every step, doesn't that induce catastrophic semantic drift?
You mean, does it turn into garbage?
Yeah. If an adversary ruins the underlying payload to evade the detector, the defender still technically wins by forcing the attacker to produce unreadable adversarial gibberish.
The researchers anticipated that exact critique. They didn't rely on subjective heuristics to measure the degradation of the payload.
They quantified the semantic fidelity using rigorous multi-tiered evaluation frameworks.
Yes. They deployed MTurk human evaluation studies to measure perceived quality.
And they cross-validated those findings using strict, automated machine comprehension benchmarks.
And the empirical data they extracted is deeply concerning for the viability of text detection.
Here's where it gets really interesting, because if the adversary can mathematically decouple the text from the detector's distribution mapping without destroying the semantic utility of the payload, the entire detection paradigm collapses.
And the data supports that collapse.
Wow.
When human evaluators assessed the recursively paraphrased outputs using a strict Likert scale, 77% of the passages were classified as exhibiting high-quality content preservation.
77%.
The core assertions, the factual data points, and the logical flow survived the recursive laundering intact.
That's incredibly high.
Furthermore, 89% of the laundered passages retained high-quality grammatical coherence. The text did not devolve into a random bag of words.
Human evaluation is notoriously subjective, though. Did they test the semantic retention against a deterministic NLP benchmark?
They did, and this is perhaps the most striking data point in the evasion methodology.
Okay.
They subjected the recursively laundered text to the Squad V2 benchmark,
which is a highly rigorous reading comprehension dataset designed to test whether an AI can accurately extract answers from a given context passage.
Exactly. They took the original human context passages, replaced them with the 5 times recursively paraphrased AI versions, and then prompted a separate evaluator AI to answer complex questions based on the new laundered text.
And the accuracy of the extracted answers.
Maintained an incredible 97% baseline.
97%.
The semantic entropy introduced by 5 rounds of recursive paraphrasing was a mere 3%.
So, an adversarial actor running a massive disinformation campaign can generate thousands of synthetic news articles,
Yes.
dynamically launder them through a local Lame2 instance until the watermarks and log probability signatures are entirely neutralized,
Yep.
and the resulting payload will still successfully manipulate the target audience. The evasion vector is empirically proven.
It is. Evasion completely neutralizes the defensive utility of these systems, resulting in an unmanageable spike in type 2 errors, failing to detect the machine text.
Right.
However, the researchers pivot the threat model to an even more damaging vulnerability: the deliberate triggering of type I errors.
This is the spoofing attack vector.
Yes, evasion is about an adversary hiding their own tracks. Spoofing is about an adversary actively manipulating the classification boundaries to frame an innocent human author.
Let's examine the mechanics of spoofing. If we look at the soft watermarking pillar, you explain that the steganographic green list is generated by a cryptographic PRNG. If an attacker does not possess the private key to that PRNG, how is it mathematically possible for them to generate a human-written text sequence that the detector authenticates as possessing the watermark?
The researchers engineered a brilliant proof of concept, demonstrating that you don't need to steal the private key.
Really?
You can reverse engineer the statistical boundaries of the green list through an adaptive querying attack.
Okay, how does that work?
They treated the watermarked OPT 1.3b model as a black box oracle and executed 1 million automated queries against it.
Just hammering the API.
Exactly. By compiling this massive corpus of watermarked output, they could perform a targeted statistical analysis on the token pair frequencies.
Analyzing the transition probabilities between tokens to map the PRNG's behavior.
Yeah.
Do they have to map the entire vocabulary space? I mean, which could be tens of thousands of tokens.
No, and that is what makes the attack so efficient. They restricted their statistical analysis to just 181 of the most common English words.
High-frequency function words and common nouns.
Yes. They tracked the token pair statistics for just this narrow subset.
Give us an example.
For example, they would isolate every instance where the token the V was generated and tally the frequency distribution of the immediate subsequent token.
Because the PRNG mathematically biases the AI to select from the hidden green list, a massive statistical anomaly emerges over 1 million queries.
Exactly.
I see the architecture of the attack now. In a normal unwatermarked distribution, the word first might follow the word the perhaps 5% of the time.
Sure.
But if first happens to be assigned to the green list by the PRNG whenever the seed token is the frequency in the watermarked corpus might spike to 25%.
Precisely. By identifying these massive frequency deltas, the attacker doesn't need the cryptographic key.
They can simply deduce the steganographic mapping.
They mathematically derive a proxy green list.
Proxy green list.
Armed with this proxy mapping, an adversary can manually author a completely original, human-written text block.
But consciously constrain their vocabulary choices to align with the token pair sequences identified in the proxy list.
Yes. When the researchers submitted this manually spoofed human-written text to the official watermark verification API, the results were catastrophic.
How bad?
The detector's AUROC collapsed from a highly confident 99.8% down to an abysmal 1.3%.
1.3%.
The steganographic verification system was entirely compromised, definitively classifying a human text as a machine-generated watermarked output.
The socio-political implications of that vulnerability are massive.
Huge.
A state-sponsored adversary or a malicious corporate actor could utilize this proxy green list to manually author highly toxic, illegal, or defamatory content.
Yes.
They publish the payload and then point to the target company's own watermarking API, which cryptographically verifies that the toxic content was generated by the company's proprietary LLM.
It transforms a safety feature into a weapon for reputational destruction.
It really does.
But the reputational risk to foundational model developers is severe. But the spoofing vulnerabilities extend beyond just watermarks. The researchers also exposed a critical structural flaw in the retrieval-based detection systems.
The databases.
This raises an important question regarding the massive data privacy and security assumptions inherent in logging every generated token to build a detection database.
So, referring to the fourth pillar, the brute force semantic search systems that log everything, how does an adversary spoof a database lookup?
The researchers outline a highly practical adversarial scenario that exploits the very nature of a centralized retrieval log.
Let's hear it.
Consider a localized adversarial environment. A malicious teacher who wishes to systematically frame a specific student for academic fraud.
Okay.
The student writes a completely original, rigorously researched essay, totally independent of any AI assistance, and submits it to the teacher.
And then?
The malicious teacher takes that human-authored document, inputs it into the school's approved LLM, and prompts the model to execute a standard paraphrasing task on the text.
And because the retrieval-based detection system is continuously logging every single interaction to build its defensive database.
That newly generated, paraphrased iteration of the student's original essay is now permanently indexed within this system.
Oh my God. The attacker is poisoning the database with the victim's own semantic payload.
The trap is perfectly set. The following day, the malicious teacher submits the student's original human-written essay into the institution's retrieval-based AI detector.
The detector executes its FAI similarity search,
Scans the millions of logged outputs, and immediately identifies a high-confidence cosine similarity match with the paraphrased version the teacher generated the night before.
and the detector definitively flags the student's original work as AI generated.
In the empirical tests conducted by the researchers, this specific semantic spoofing attack achieved a 100% success rate.
100%.
100%.
The detection infrastructure is completely weaponized against the end user. The panopticon built to catch automated cheating is trivial to exploit for targeted harassment.
A malicious manager framing a subordinate.
A rival journalist burning a competitor's credibility.
It's all on the table.
The empirical data proving that these four pillars can be evaded and spoofed is damning. But what elevates this paper from a simple cybersecurity vulnerability report to a foundational alignment thesis is Section 4.
Ah, yes.
The authors don't just demonstrate that current engineering is failing, they present a formal mathematical proof that reliable detection is theoretically impossible in the limit.
Section 4 is the crux of the paper. It shifts the discourse from empirical stress testing to rigorous statistical theory.
Theory that fundamentally changes the game.
The authors deploy a mathematical framework to establish an absolute upper bound on the performance of any possible detection algorithm.
Regardless of the underlying engineering or future advancements in neural network architecture.
Right. To grasp this proof, we have to deeply understand the concept of total variation distance.
Now, I am not going to apologize for getting into the math here, because understanding this equation is mandatory for anyone seriously discussing AI safety policy.
It really is.
Walk us through total variation distance, or TV distance, in the context of probability measures over a text space.
In formal terms, total variation distance is a metric utilized in probability theory to quantify the distance between two probability distributions.
Okay, let's break that down.
Let's define P as the complex, high-dimensional probability distribution of all human-written text.
Which encompasses our entire syntactic range, our vocabulary constraints, our structural quirks.
Exactly. Now, let's define Q as the probability distribution of text generated by a specific language model.
So P is human, Q is AI.
Right. Total variation distance mathematically represents this supremum, the absolute largest possible difference between the probabilities that these two distributions assign to any single generated text sequence.
Okay, if we visualize this geometrically, imagine two massive probability density functions, two high-dimensional bell curves.
Okay.
If we are evaluating a primitive early generation Markov chain model, its distribution Q looks nothing like the human distribution P. The geometric overlap is minimal,
The supremum is large.
meaning the TV distance is close to 1.
Building on that geometric visualization, the entire teleological purpose of foundational language modeling is to optimize the model's loss function such that the generated distribution Q perfectly mimics the human distribution P.
That's the whole point of AI scaling.
As model parameters scale, and as reinforcement learning from human feedback is aggressively applied, the AI's probability density function shifts and morphs.
Directly overlapping the human distribution.
Yes. The mathematical consequence of this optimization is that the TV distance between P and Q strictly monotonically decreases towards 0.
Which brings us to Theorem 1.
Theorem 1.
The authors formally bound the classification accuracy of an optimal discriminator using the shrinking TV distance. What is the precise formulation of the upper bound?
Theorem 1 states that for any possible detection algorithm functioning as a binary classifier between distributions P and Q, the absolute maximum area under the ROC curve, the highest possible AUROC it can achieve, is strictly less than or equal to 1/2 plus the TV distance minus the TV distance squared divided by 2.
Okay, let's analyze the limits of that equation. We established that the core objective of generative AI scaling is to push the TV distance to 0.
Right.
If we evaluate the limit of that bound as TV approaches 0, the entire numerator of the second term 0 minus 0 squared collapses to 0.
Yes.
The equation fundamentally reduces to AROC is less than or equal to 0.5.
And an AROC of 0.5 is the statistical definition of a random guess.
It is a coin flip.
Theorem 1 rigorously proves, drawing on the Neyman-Pearson lemma, that as the probability distribution of a language model converges with the distribution of human text, the predictive power of even a theoretically omniscient, mathematically perfect detector converges to random chance.
Wow.
It is not an engineering deficit, it is an absolute mathematical limit.
So what does this all mean? It means the entire venture capital ecosystem pouring hundreds of millions of dollars into next-generation AI text detection startups is fundamentally chasing a mathematical ghost.
They are trying to beat math.
You cannot out-engineer a shrinking total variation distance. But a skeptic might argue that while this is a beautiful theoretical proof, actual LLMs might not be minimizing TV distance in practice.
Right, theory versus practice.
Did the researchers provide empirical validation that the TV distance is actively shrinking across current state-of-the-art models?
They absolutely did, calculating the exact total variation distance between two massive high-dimensional natural language distributions is computationally intractable in a direct manner.
So what did they do?
They designed a rigorous projection experiment. They utilized a massive data set of organic human text, specifically the web text corpus.
Okay.
They then generated corresponding text distributions using a progression of OpenAI's models, specifically GPT-2 small, GPT-2 medium, GPT-2 large, and GPT-2 extra large.
So by evaluating a single architectural family across varying parameter counts, they isolate the variable of scaling.
Exactly.
How did they approximate the probability density functions to calculate the TV distance?
They employed a sophisticated dimensionality reduction technique using meta tokens. They mapped the complex vocabulary down to a finite set of syntactical and semantic meta tokens,
allowing them to calculate empirical probability density functions that served as a proxy for the true distributions.
And the empirical results perfectly mirrored the theoretical proof.
The TV distance shrank.
As the parameter count increased from the small model up to the extra large model, the measured total variation distance exhibited a strict monotonic decrease. The AI's distribution was measurably absorbing the human distribution.
The empirical data validates the mathematical bound. As models scale, TV shrinks, and the detection bound collapses towards 0.5.
It's inevitable.
If we accept the finality of Theorem 1, we must fundamentally reevaluate how we deploy these systems today. Let's analyze corollaries 2 and 3 from the paper's appendix, which detail the inescapable trade-offs mandated by this mathematical reality.
Corollaries 2 and 3 mathematically formalize the type I and type 2 error seesaw.
Explain that seesaw.
If you look at the geometry of the receiver operating characteristic curve, bounding the AUROC fundamentally constrains the relationship between your true positive rate and your false positive rate.
Because the human and AI distributions are geometrically overlapping, a structural trade-off is unavoidable.
Exactly. If an enterprise compliance department demands a highly sensitive detector optimized to catch all AI-generated text, meaning they are deliberately minimizing their type 2 error or evasion rate, they must artificially lower the classification threshold.
But because the distributions overlap heavily due to the minimized TV distance, lowering that threshold mathematically forces the detector to cast its net into the overlapping area.
Yes.
The system is structurally mandated to flag human-authored text that simply happens to fall within the overlapping probability space. You are mathematically guaranteeing a massive spike in type I errors false positive.
And the human distribution is vast. Some individuals naturally write with highly structured, predictable syntax,
utilizing low perplexity vocabulary that sits precisely in the valleys of the zero-shot probability map.
If you optimize the detector sensitivity to catch evasive machine text, the mathematics dictate that you will increasingly misclassify these highly predictable human writers as machines.
As the TV distance continues to shrink, that overlapping zone expands.
Meaning the volume of innocent humans swept up in the false positive net will scale exponentially.
This transitions the discussion from mathematical theory to severe socio-technical impact.
This is the real world.
This is the exact dynamic driving the crisis in academia and professional publishing right now. Institutions are purchasing these black box detection APIs and deploying them as infallible truth oracles.
It's dangerous.
We are seeing massive controversies, such as the widely documented instances where Turnitin's proprietary AI detection algorithms falsely flagged vast swaths of legitimate student work,
leading to academic suspensions and frozen grades.
The institutions treat the algorithm's output as cryptographic proof, completely ignorant of the fact that they are essentially executing a weighted coin flip against the overlapping probability distributions of human and machine text.
Deploying systems bound by Theorem 1 to adjudicate academic or professional integrity is deeply problematic.
Very.
Now, the authors are intellectually honest about the edge cases. They note that recursive paraphrasing, while statistically devastating to detectors, can introduce minor semantic entropy.
That might require brief manual human intervention if the payload demands absolutely pristine, publication-grade academic formatting.
However, for the overwhelming majority of adversarial threat models, automated SEO poisoning, programmatic spear phishing, synthetic social media amplification, and general academic fraud, the automated laundering is more than sufficient.
Right. The manual fixing of a stray comma or a slightly awkward prepositional phrase doesn't invalidate the fact that the algorithmic detection layer has been entirely bypassed.
The adversary simply runs a spell checker over the laundered text.
Yeah.
If we connect this to the bigger picture of alignment research, this paper serves as a vital structural reset.
A wake-up call.
For the past several years, the industry has been paralyzed by the hope of a post-generation software patch. We wanted a lightweight API that could passively ingest text and definitively separate human truth from synthetic noise.
And Sadasivan and his team have effectively proven that as long as we treat AI safety purely as a post-generation text analysis problem, we are playing a game constrained by mathematical laws we cannot defeat.
We are destined to lose that game.
Let's synthesize the architectural vulnerabilities we've mapped out in this deep dive. The foundational pillars of AI text detection are structurally compromised.
Completely.
Supervised neural networks, zero-shot log probability maps, steganographic watermarks, and retrieval-based indexes are brittle.
They are systematically evaded via recursive paraphrasing, which launders the statistical signatures without destroying semantic utility.
They are actively weaponized via spoofing attacks, allowing adversaries to reverse engineer proxy green lists or execute semantic collusions in retrieval databases to frame innocent human authors.
And underwriting all of these vulnerabilities is Theorem 1.
The mathematical proof that as total variation distance shrinks in the pursuit of more capable language models, the predictive power of any post-generation detector asymptotically approaches random chance.
The conclusion is inescapable. The text itself, the discrete sequence of tokens, contains mathematically insufficient signal to verify its own provenance.
Which brings us to the theoretical frontier. It is time for our novel notions segment.
Always my favorite part.
This is where we synthesize the hard empirical data from the paper and extrapolate an outlandish but logically rigorous new research vector for AI alignment and safety.
Let's hear it.
Please note, this final segment is purely theoretical and for entertainment purposes only. So, if analyzing the semantic and statistical content of the text is a mathematical dead end due to Theorem 1, how do we architect a system to verify human truth in a synthetic ecosystem? Pitch me your novel notion.
My novel notion accepts the finality of Theorem 1 and completely abandons the semantic analysis of the payload.
Okay, abandoning the text entirely.
If the content of the text will inevitably become indistinguishable from human writing, the alignment community must pivot its focus to the physics of computation.
The physics.
I propose a global research and regulatory agenda focused entirely on hardware-level cryptographic provenance.
Moving the security perimeter away from the software layer and directly into the silicon. Walk me through the technical architecture of hardware provenance.
We mandate a fundamental architectural shift at the foundry level. Every single GPU, TPU, or specialized ASIC manufactured for tensor operations and AI inference is required to execute a cryptographic microstamping protocol at the hardware layer.
Built right into the chip.
Exactly. We utilize advanced zero-knowledge proofs, specifically Zsk snarks, embedded directly into the silicon's instruction set.
And as the GPU executes the matrix multiplications to generate a sequence of tokens, the hardware itself generates a cryptographic signature.
That encapsulates the specific silicon die ID and the temporal data of the compute cycle.
The crucial element of utilizing a zero-knowledge proof is that it cryptographically guarantees the hardware origin of the compute cycle without revealing the underlying prompt data, the model weights, or the specific text generated.
Preserving absolute data privacy for the user while definitively proving machine generation.
Exact.
The ZK snark signature is then immutably bound to the file metadata of the generated text block and verified against a decentralized immutable public ledger.
So when an end user reads an article or a teacher receives a digital essay, the client software does not waste compute cycles executing a flawed semantic analysis of the words.
It simply interrogates the metadata.
Yeah.
It asks, does this text block carry a valid cryptographic signature from a registered tensor core?
We are no longer trying to detect the ghost of an AI in the text.
We are tracking the digital physics of the compute power used to create it.
That architecture completely circumvents the type I and type 2 error seesaw established by corollaries 2 and 3.
It does.
Because you are actively removing the probability distributions of the text from the verification equation, the total variation distance becomes entirely irrelevant.
A human author typing on a standard laptop keyboard is not routing their keystrokes through the matrix multiplication units of an H100 GPU.
Therefore, there is zero cryptographic signature generated. The false positive rate, the mathematical guarantee of falsely accusing innocent humans, drops to absolute zero.
Furthermore, it inherently neutralizes the recursive paraphrasing evasion vector.
Oh, because if an adversary attempts to launder their generated payload through a secondary AI model to scrub statistical fingerprints,
That secondary inference run will simply trigger the hardware to attach a brand new ZK snark signature to the new output.
the hardware provenance is recursive by default.
Exactly. The only conceivable physical method to evade the hardware stamp would be for the adversary to read the generated text on a screen and physically transcribe it, keystroke by keystroke, on an unmonitored machine.
Which fundamentally breaks the economic scalability of generative AI.
It ruins the ROI for the attacker.
The entire point of using an LLM for a massive disinformation campaign or SEO spam operation is the near zero marginal cost of automated generation.
If the attacker is forced to employ a massive human workforce to physically transcribe the machine's output just to bypass the hardware metadata, they have lost the asymmetrical advantage of the compute.
It treats AI capability as a highly regulated, trackable physical resource, much like enriched uranium, rather than treating it as an untrackable digital abstraction.
It represents an extreme paradigm shift that would require unprecedented cooperation between silicon foundries, open source developers, and international regulatory bodies.
True.
But given the absolute mathematical limits proven by Sadasvan and his team, hardware-level cryptographic provenance might be the only structurally sound path forward to maintain ground truth in the digital era.
Thank you for navigating this complex theoretical architecture with us on this deep dive.
It was a pleasure.
I highly encourage you, the listener, to evaluate the digital text you consume through a new lens today. The mathematical reality is that the semantic boundary between human and machine is collapsing much faster than our software algorithms can adapt.
And the detection systems we trusted to protect our digital integrity are structurally compromised.
Remember, the link to the original University of Maryland research paper is in the bio and description for your own deeper technical analysis. Until next time, stay curious and rigorously question the algorithms.